I hadn't been in Moscow for quite a while, and I was down in the center of Moscow, near the Kremlin, and getting back turned out to be a very, very challenging endeavor. The traffic in Moscow is almost as bad as the traffic in Los Angeles. Not quite, but almost. I hope to be able to make it up to you. I'm going to shorten my presentation for a little bit to keep try and keep the program on time. I imagine most of you know about the detection of gravitational waves with binary black holes that the LIGO scientific collaboration and Virgo collaboration made earlier this year, and actually the detections were last year. I'm going to sort of tell you the scientific story of that. So I will start with a primer, an overview of what gravitational waves are, why we study them. I'll spend time talking about LIGO, the LIGO detector. I will spend more time talking about the first observations of gravitational waves from binary black holes. And I'll conclude with what I think is the most interesting, or one of the most interesting frontiers of gravitational wave science, using gravitational waves in conjunction with photons and neutrinos to study cataclysmic astrophysical processes, so-called multi-messenger astronomy. So let me begin. This is a one-slide introduction to gravitational waves and general relativity. Einstein, a little over 100 years ago, postulated this famous equation, and I will not go into too many details about the equation, but I want to say three things. On the left-hand side is geometry. It is space and time, encoded in something called the Einstein tensor G mu nu. And I apologize for the notation. This is just historical. This is a tensor, that is the gravitational constant, Newtonian gravitational constant. On the right-hand side, that quantity T mu nu is matter and energy. So the equation, and the brilliance, if you will, of Albert Einstein, was to recognize that matter and energy and space and time are in fact coupled to one another. That matter and energy can affect space and time, the geometry of space and time, and space and time can in turn affect the way matter moves. But the coupling constant is this quantity 8 pi g over c to the fourth, and that number is very tiny. It's about 10 to the minus 42, give or take. All right, so that means you need a lot of matter and energy to affect a very tiny change in space and time. Now, gravitational waves fall out of this equation by making a couple of assumptions. First is propagating in free space. So I set the right-hand side of the equation to 0. And then I assume we have a geometry that is mostly Minkowski or mostly flat. So the metric tensor that goes into this equation, or this side of the equation, is just Minkowski plus a small perturbation. You go through about 5 or 6 lines of algebraic manipulation, and you end up with a wave equation. And the wave equation is for the strain of gravitational waves. I can solve that wave equation. It is basically propagating waves outward. I made some assumptions about the gauge I'm working in. I work in the transverse traceless gauge, and it turns out there are 2 independent components, and we call them the cross and the plus strain. And if a gravitational wave were propagating in U, this is what you would see. All right, physically, it's a strain, change in length per unit length, and what it does is it stretches and compresses space-time orthogonally to the propagation direction. So, looking right here, you can see that the vertical axis is stretching while the horizontal axis is compressing, and on every alternate half cycle, it flips around. The other thing you can see is that if you're at the ends of those arrows, all right, there's a lot of motion. But if you're near the arbitrary reference point, there's not a lot of motion. And that's basically the fact that we're not measuring just displacements, but gravitational waves are physically strains. So this immediately says a couple of things if you want to try and measure them. says you want to measure over long baselines. You want that L to be as big as possible to make your sensitivity to a strain as small as possible, or as big as possible, and you want the displacement to be measured as small as possible. If I go back into that equation and put the source term back in, you calculate that the strain arises from the second time derivative of the quadruple mass moment. And there's that factor g over c to the fourth, which necessarily means that these waves are going to be very tiny. I can take a sample condition, much like we would measure if we were looking for black holes. If I take two objects, separate them by a few Schwarzschild radii, put about 10 solar masses into each of them. This equation here reduces to this equation here. If I go, the distance r is the distance from the source to the observer, and that's very important. The gravitational waves fall off as 1 over the distance, not 1 over the distance squared. That will turn out to be very handy and helpful for us. Anyway, you put everything in there, and what you find is that this strain is about 10 to the minus 21. And the orbital frequency that I assumed, the omega orbit that I assumed to get that, is about a few hundred hertz. And this represents a real physical condition that you would get if you had two black holes orbiting one another. Right. Why are they interesting to study? Well, making them in a laboratory is essentially impossible. The strains are much, much smaller than 10 to the minus 21. But making them in nature with cataclysmic astrophysical events is not impossible. And so there are 4 classes of sources we look for. The coalescing binary systems, I'll say more about these. These would be black holes that we discovered, or perhaps neutron stars. They produce a very specific kind of waveform that we can model. There's also waveforms that are transient, burst, we call them burst sources. And we don't know enough physics to model them properly, so we search for them in a slightly different way. 2 good examples, astrophysical examples, would be supernova or cosmic strings. Both supernova and cosmic strings, or collapsed supernova, would produce weakly gravitational waves, as cosmic strings would as they go through each other and they break. And at the cusp of the cosmic string, they would produce a gravitational wave. We also search for the cosmic gravitational wave background. This would be the analog, if you will, of the cosmic microwave background. A very powerful probe of cosmology, because unlike the CMB, gravitational waves basically were emitted at almost the moment the universe was born in the Big Bang. They're probably difficult and perhaps even impossible to detect by LIGO. Nevertheless, we search for them, because if we see something interesting there, I think it would revolutionize cosmology. Finally, continuous sources. So these would be spinning neutron stars or pulsars that have some sort of mass asymmetry, perhaps a crustal defect. Okay. Why are they interesting to astrophysicists? Well, there are a number of reasons. First, there are a number of questions that you can answer in fundamental physics with gravitational waves. First question is general relativity the correct theory of gravity? If we detect gravitational waves that aren't consistent with general relativity, it means that either general relativity is wrong or there's some extension to general relativity that we have to put in place. How does matter behave under extreme gravity? Are black holes truly bald? In other words, are they truly Einsteinian black holes, only possessing mass and angular momentum? A whole host of questions in astrophysics, astronomy, and cosmology. Short, hard gamma ray bursts are thought to be created from binary neutron star mergers. When at the merger point, basically the dynamics of the magnetic fields explode, the subsequent merger of those 2 neutron stars basically forms a gamma ray burst, a short, hard gamma ray burst. Now, we've seen lots of short, hard gamma ray bursts, but we've never seen a binary neutron star merge. So if you could see them both at the same time, you'd have a smoking gun. What's the mechanism for a core collapse supernova? That's a question. We know neutrinos seem to be the main energy carrier, but if we could map out the mass distributions as a core collapse supernova is happening by monitoring the gravitational wave that it emits, we might learn something more about that process. How many low-mass black holes are there in the universe? We can detect black holes using X-rays, now we can detect them using LIGO. So we're going to start really filling in the mass spectrum, the population of stellar mass black holes. Let me just pick a few other ones. How bumpy are neutron stars? In fact, can you see crustal deformations from neutron stars? And there are a number of other questions here. I focus on these two questions that I put in bold because, in fact, the first two detections that we made with LIGO actually, in some sense, start to address those questions. Okay, so now let me talk a little bit, so that's enough of the introduction. Now I want to talk a little bit about the detector and LIGO itself. LIGO is actually two observatories, one in Hanford, Washington, the other in Livingston, Louisiana. And in addition, we have laboratories at Caltech and MIT, and I happen to be at Caltech. There's about 180 staff members who work at the observatories at Caltech and MIT. There's a much larger group of people, the LIGO Scientific Collaboration, of which there are members in the audience from Moscow State University, from the Institute of Applied Physics. This is about 1,000 scientists from 80 different institutions, 15 different countries, including Russia. And we do the science of LIGO. And in fact, all the people, most of the people in the LIGO laboratory are part of the LIGO Scientific Collaboration. There's just some nice pretty pictures. This is the Livingston Observatory, the laser, and most of the equipment is in here. You go about 4 kilometers, so that's the distance, our baseline for measuring the stretching and compressing of space-time. And you have an end station up there. So there's mirrors here and alternatively over there. Just to give you a different perspective on LIGO, this is the identical, literally it's an identical facility, but it's just at a different place. This one is in Hanford, Washington. Okay, so now let me give you I would call it a heuristic argument for why you can use interferometers to measure gravitational waves at the strain that I told you at the beginning, 10 to the minus 21. So this is a famous Michelson interferometer. There's a laser, there's a beam splitter, there are 2 end mirrors, we call them test masses, and then there's a photodetector. All right, and ordinarily, the laser light comes out, it splits at the beam splitter, half of it goes this way, we'll call this the Y arm, half of this goes this way, we'll call it the X arm. It comes back, and we make the distance, the differential distance between this point and this point, the Y arm and this point, the X arm, we make it such that the interference pattern comes back and the light goes towards the laser. That's for technical reasons, but it's important to do. All right, so you can ask yourself, with using this interferometer, how good can you make a strain measurement? And if you think about it, there are only 2 real lengths in this problem. All right, that's the wavelength of light, and that's the length of the arms. I told you the length of the arms is 4 kilometers. The wavelength of the light we use is about 1 micron. That's the laser that we use. And you can very quickly calculate that you're nowhere near 10 to the minus 21 with that. So you have to play some tricks, all right, or you have to enhance the sensitivity of your interferometer. And the first way we do that is we put in fabric Perot cavities. So we put on 2 more mirrors in the arms, and we keep those mirrors on resonance such that, and we can dial, if you will, the number of round trips that light makes once it gets into the cavity by changing the reflectivities of these mirrors. And basically what this does is this enhances the storage time of the light in the cavity by about n, where n is the number of round trips that the light makes. And I should also point out here that the reason this argument works and the reason LIGO works is because the period of the gravitational wave, all right, that we detect is actually much longer than the 4 kilometers. And so what we have to do is we have to keep, and the storage time of the simple interferometer. So what we want to try and do is enhance the storage time of the light in the interferometer such that we sample, say, a quarter of a cycle of the gravitational wave. All right, so we do a little bit better. This number can be made, in principle, up to 10,000. In practice, we only go up to about 300, maybe a little less. And then the last thing we do is we put another mirror in the cavity, and this basically is the power recycling mirror. All the light that comes back here, recall I said no light goes in that direction, all the light that comes back here can be resonantly re-injected back into the interferometer. And what this does is it basically enhances, well, it enhances the storage time, but it also enhances the number of photons that hit the beam splitter. All right, and if you do that calculation for the numbers that we use, one micron, 4,000 meters. In our case, like I said, the round trip number of round trips here is about 300, a little less than that. The number that you get is 10 to the minus 22. So that's, in some sense, sort of a simple back-of-the-envelope calculation, and you can make an interferometer that will detect strains at the level that we need to detect. And I'll point out that an advanced LIGO, at its design point, we use 125 watts of light, but because of these resonant cavities, we end up with 800 kilowatts of resonant light in the cavity, average power, when the cavities are locked. That's a lot of light, and it turns out that creates problems. And I'll tell you about one of them in a minute, because it was something that we discovered. Actually, it was Professor Reitze that discovered that problem. So, all right, now, where did this idea for interferometers come from? Well, it came from a paper that was published in the Journal of Experimental and Theoretical Physics back in 1962 by Gerstenstein and Pustervoigt. And the key phrase here is they realized that in the low frequency range, it should be possible to detect gravitational waves by a shift in the bands of an optical interferometer. In other words, you could use an optical interferometer to measure gravitational waves. Up until this time, the preferred method, the other method, was using resonant bar detectors, which were narrow band detectors. This was an important paper, and it got people around the world, particularly in Scotland, Ron Drever, and in the United States, Ray Weiss, thinking about how you would make an interferometer that could detect a gravitational wave. And in both cases, eventually that became LIGO. Okay, so from this idea to this very simple picture of the interferometer, and it's not great pictures here, but I'll just walk you through some of this. So this is the laser. You'll recognize the laser, the beam splitter, the end mirrors here, the power recycling mirror, and the signal recycling mirror. All of these other components in the detector are basically there to make the laser very clean, very pure, to keep the mirrors at their operating points. And so there are a number of things here. First, we start with a very powerful, very stabilized laser system developed by the Albert Einstein Institute in Germany. We then phase modulate the light. That provides RF sidebands that are used for sensing and locking the positions of the cavities and the mirrors. And there's a very important component that was designed and built in Russia, and that's the Faraday isolator here. It was built at the Institute of Applied Physics in Nizhny Novgorod. There are active seismic isolation systems to keep the noise, the vibrations from vibrating the mirrors. We then go a step further. The mirrors are actually suspended. The mirrors themselves are 34 centimeters in diameter, about 20 centimeters long. They're 20 centimeters thick. They are made of fused silica. They weigh 40 kilograms. And we suspend them on optical fibers. That's the mirror. There's another, we call it a penultimate mass above it, and there are fibers that suspend that. There are conditioning systems, input optics, which is all of this stuff, output optics, this is a cavity filter here. And then we also have auxiliary lasers that we use to lock the cavities independently. All right, and again, this is a quite simple picture, but it gives you a flavor of the technologies and engineering that goes into this. All right, so in order to make this work, you have to understand where the measurement noises come from. In other words, what kinds of things will affect your measurement of the displacement, or what kind of things will affect the photon counting that you do at the photodetector. And so they fall under displacement and sensing noises. Displacement noises, there are a number of seismic noise. The ground is moving, mostly due to natural seismic activity, mostly due to actually the microseism, due to earth tides. There's radiation pressure, photons. Remember I said 800 kilowatts of power, right, are in the arm cavities when at full design sensitivity. All of those photons carry momentum with them, and they arrive at random times due to photon statistics. Therefore, they kick the mirror, and that's a noise source at low frequency. There's thermal noise, and this is basically the fact that the mirrors are at finite temperatures. Suspensions and optics both have that. In fact, the big one is coatings. And then there's a very interesting noise source, Newtonian noise, or dynamic gravity gradient noise. The fact that the Earth is moving, there are body surface waves, seismic surface waves coming through, the density perturbations from those seismic surface waves actually, of course, introduce changes to local gravity. The local gravitational field changes, and that can push the mirror around. And then there are sensing noises, and these break down into two classes. One is shot noise, Poisson statistics. The fact that the photons are not classical objects, they're quantum objects, therefore they have the Heisenberg uncertainty principle that they have to obey, and it manifests itself as arriving in random times. And then there's also residual gas noise. So we have to operate the interferometer in a vacuum, and the level of that vacuum is set by the amount of scattering of the light off of the residual molecules in the vacuum that we're willing to tolerate. And then there's also technical noises, and that's lots of them. So this curve summarizes our modeling of all of those noises, and I'll actually walk through it just a little bit to calibrate it. On the x-axis is frequency. So this is 10 hertz, this is 1 kilohertz. So in some sense, the detection bandwidth of our interferometer goes from 10 hertz to about 5 kilohertz. And then on this axis is strain, so it's the delta L over L in units of 1 over per root hertz. So in other words, it's an amplitude spectral density. And then you see all of the noises that are up here, and they all correlate to some one of these things. The big ones that we have to worry about are radiation pressure, and there the signal to noise goes as 1 over the square root of the power. In other words, if I turn down the power, I turn down the number of photons that are hitting the mirrors, and therefore I turn down the random jockeying of the mirrors. At high power, I'm limited by photon counting statistics, photon shot noise. There, I want to turn up the power. So you already have sort of an inherent contradiction that the good high power sensitivity, you want, or high frequency sensitivity, you want large numbers of photons. To get the good low frequency sensitivity, you don't. All right? And there's a way out of that involving squeezing. And then in the center, where most sensitive part of the spectrum, it's basically what I call statistical mechanics, or KT physics. The fluctuation dissipation theorem tells you how much energy that you put in all of the different frequency bands from resonances in your mirrors and things like that. And that's given by here. And then there are also technical noises that I won't go into, but there's lots of them. Anyway, you put this all together, all right, and we decided that we would start a run with our interferometer operating at about 25 watts. So that corresponds to about 100 kilowatts in the cavity. And this is an experimentally measured spectrum. So again, that's 10 hertz, 1 kilohertz. This is displacement now, not strain, but if you want strain, you just divide this number by 1,000. So the displacement sensitivity, that's the delta L, if you will, in units of meters per root hertz, is better than 10 to the minus 19 over the band from about 40 hertz to about 1 kilohertz. So this is a remarkably precise measurement. And the curves that you see underneath are the modeled noises, and you can actually see that there's a couple places where we don't understand what those noises are yet, and that's an area of active research. All right, so we spent a lot of time building this interferometer. We spent a lot of time commissioning it. We turned it on. And when we turned it on, before I do that, when we turned it on, we actually started seeing signals. Let me talk about that effect that I told you that comes from operating at high power. And this was an effect that was predicted by Vladimir Reitze and his group, Sergei Vichanin, I believe in the early 2000s. And it's a really interesting physics problem, but it's really bad it's really bad for our detector. So while this is great physics, it's not good for gravitational detectors. And the idea is quite simple. It comes back to this idea of radiation pressure, but not quantum radiation pressure in this case, just classical radiation pressure. If I have a mirror, that mirror has acoustic modes that are basically driven thermally, the fact that it's a finite mirror, and the final temperature. And the laser beam, when it hits the mirror, can actually pump energy into those modes. And this is a feedback process, so there's a feedback loop that exists here. So I have a thermal excitation which drives some mechanical mode, in this case it's sort of a 1-0 mode of the mirror, right? That interacts with the Gaussian laser beam from the arm cavity, all right? What happens is when the beam hits the mirror, it generates basically this dynamic acoustic mode. The mirror is actually moving at a very tiny level. It produces a higher order optical mode in the cavity, which of course has radiation pressure, which starts pumping more energy into that mode, and you go round and round and round, and eventually you get to the point where so much energy is being dumped into this higher order optical mode that's in some sense, resonantly coupled to the acoustic mode, that the interferometer no longer works. And fortunately, the fact that Professor Brzezinski pointed this out to us a long time ago allowed us to come up with strategies for dealing with it. And here is the equation that governs the parametric gain. So for a particular mode, M, all right, basically the gain is proportional to the arm cavity power. It's inversely proportional to the mass of the mirrors and the square root of the mode frequency. And here's where the action takes. There's 2 parts here. First, the mechanical Q factor, in other words, how stiff that mode is, and then the overlap between the optomechanical mode and the gain of that mode in the system. And here's a good example of an optical mode that couples to an acoustic mode. The overlap function here, this is only about 0.1%, 0.1, so 10%. But in fact, when you turn this is time and access. This is laser power at 50 watts. And you can see after a period of time, there's a time constant associated with each of these modes. The mode starts to ring up. So it has a ring up time of about 240 seconds. And in order to kill it, in order to get rid of the mode, you have to turn the laser power down, which is not what we want to do, but you see that starts to turn it over. There's a little bit of saturation in our electronics. You go back to about 10 watts here, a little bit more than that, and you see the mode eventually rings down. So you can suppress these modes by turning the laser power down, but that's bad. You don't want to do that. So there are other ways to get rid of it. One is basically to change the radius of curvature of the mirror. That changes the optical mode spacing. The other is to do something a little more sophisticated, which is basically to pump energy into the mirror. And I won't go into the details of this unless someone asks, but we can basically inject acoustic energy into the mirror by electrostatic coupling or electrodynamic coupling. And we can use that to suppress the modes. And that works pretty well for us. So, all right, so let me move on to the first detection. Many of you may have read this paper. There are 1,004, 1,005 authors on it from the LIGO Scientific Collaboration and the Virgo Collaboration. Observation of gravitational waves from a binary black hole merger. I can tell you that this paper went through 14 revisions before it was finally published. I mean, not with a reviewer, but in our collaboration. The title was changed at least 10 times, but the part that really never changed was the bottom. These observations demonstrate the existence of binary stellar mass black hole systems. This is the first direct detection of gravitational waves and the first observation of binary black hole merger. was a pretty remarkable discovery the first time out. All right. How did we find them? Well, our interferometers are operating, so we have to search for these waves. We do it using optimal filtering. So this binary black hole system produces a chirped waveform. I'm going to try and play it for you, but I'm not sure if my computer sound is loud enough, but hopefully it will be. Basically what happens is as the black holes are orbiting one another, they're radiating gravitational waves. That causes the orbit to decay, which then increases the frequency, and then they produce more gravitational waves, and eventually the two black holes merge and form a single black hole. The problem, and it turned out not to be a big problem for our first detection, we thought it would be, is that this signal that's produced by this astrophysical source is buried in the noise. And the noise is bad for our interferometers. I mean, you look at the noise spectrum and you say it's quite good. But if we're looking for low signal-to-noise events, all right, the only way we can find those signals is by doing first coincidence measurements. You have to see the event in two interferometers. And second, it has to match some astrophysical prior knowledge. And so we have a bank of these things. Actually, we have about 250,000 different waveforms that we use to cross-correlate the data, right? And for even moderate signal-to-noise waveforms, you can clearly see that there's a signal here. So this is actually a very effective way of doing this kind of filtering. So here's the data, and this is really some of the most beautiful data I've seen. What makes this event, this is the first discovery, we called it GW150914. That happens to be the date at which it came in. This data isn't like this. This is actually data that you can see in the noise itself. So the amplitude of this wave was so great, all right, that you could do minimal filtering of the data, just some bandpass filtering. And this is what you saw at Hanford. And when you see this, and you know we've been looking for gravitational waves for a long time, you know that this is quite interesting. All right. What really gets you excited is if you look at the other detector, in this case it's Livingston. Now the Livingston detector is in a different location, and therefore the arrival time of the gravitational wave could be different. In fact, in most cases it is. So it turned out that the gravitational wave arrived at Livingston 7 milliseconds before Hanford. So basically I plotted this by putting a time shift of 7 milliseconds onto the Livingston waveform, but you can see they're entirely consistent. And that is fairly compelling. Right? The next thing you can do is you can subtract off the noise. You know the residual noise spectrum, and you can compare what's left after the noise, which is the signal, with numerical relativity. So we can calculate the waveforms that you expect to see from basically solving the Einstein field equations for two black holes on computers. And you can see in both cases, Livingston and Hanford, it's hard to see on this plot here, but the overlap between the theory, numerical relativity theory, and the data, the signal, is to the level that we can measure it exact. So this tells us something very important. It tells us that these are general relativity black holes. So these black holes look exactly like you predict from general relativity. And finally, you can plot them on time frequency plots, and that's what I showed here. The amplitude of this wave, by the way, is about, the RMS amplitude is about 4 times 10 to the minus 18 meters. So that's the distance change that we saw in the arms of the interferometer. I got rid of this, but maybe I didn't. Okay, so I'll do this very quickly. What did we see? We saw two black holes merging. One was 36 times the mass of the sun, the other was 29 times the mass of the sun. And the simulation I'm going to show you was slowed down by a factor of 1,000. All right, so this is, and by the way, this simulation is not a Hollywood or an artist simulation. It's actually solving Einstein's equations on a computer and then rendering them together. So these two black holes are orbiting. If you pay close attention, you'll see that the orbit is decaying, and they're getting close to one another and speeding up, and eventually their event horizons touch. And when they touch, they produce this burst, and that burst is basically the last gravitational wave. So what's left behind is a bigger black hole. Now that wasn't the only black hole we saw. We actually saw a second black hole on December 26th. And we saw what we think is a third black hole merger on October 12th. The statistics of that event weren't as good as we wanted. So I'll go quickly through this, but this is the other part of the puzzle that you need to be able to solve to say that you've seen a detection. It's basically, what does the foreground, in other words, the signals, look like with respect to the background? And we go through great amounts of computation to generate a background using real data by putting in time shifts that are non-physical into the Livingston data. And we do the same search. We do this cross-correlation with hundreds of thousands of templates through that entire data set that's about 5 million years long. And we know that there are no real events in there. So any of the tails are coming from coincident glitches or something like that, or pseudo-coincident glitches. So you do that, and you plot as a function of basically signal to noise. That's what this detection statistic is. All right, the background, and you can calculate the background in a couple of ways. Let's start with a black background. You can see very clearly that we have one very clean signal that should be given to 150914. This is a September event that's well above background. We can't even say what its significance is because we don't have enough data, but we can say that it's well above 5 sigma. All right, so this is an event, and that's the event that I showed you. Now the second event that we saw in December did not have such good signal to noise. It was actually about, well, so it was about half the signal to noise of this one. I can calculate the background using the same set of data, but now what I'm going to do is I'm going to remove this signal, right, because I've already called it a detection, and then you get this background, all right? And again, compare that event to that background, it's just above, it's above 5 sigma here. And then this third event is about 2 sigma, maybe a little bit less. So that's why we didn't call it a detection, right? Let's do the big one. So we can actually get parameters from these events. Let me actually go back. So we can get the masses of the black holes. We try and get the spins of the black holes. We can get the distance to the black hole. We can actually get the location of the black holes on the sky. Let me focus then on the September 15th or September 14th event. The primary mass in units of solar mass was 36. Secondary mass, that's the second component, 29. Total mass, or in other words, just the sum of those two, 65. The effective spin, this is basically the way that we measure the spins of the black holes. It looks like there's an effective spin, but the error bars are such that we can't really say that. So these particular black holes, we don't know what the effective spin of the initial black hole was. The final mass was 62 solar masses. The final spin, that's the spin of the final black hole that was left over, we don't measure that, but we calculate it using numerical relativity and from other sources. And we see that it's not quite maximally spinning, it's got a spin for about 0.68. So, of course, during this collision, a huge amount of energy is converted from space-time black holes to space-time gravitational waves. And in this case, about 3 solar masses was converted into gravitational energy. That happened in about 200 milliseconds. And so the peak luminosity was slightly more than 3 times 10 to the 56 ergs per second. And that corresponds to roughly 30 to 40 times the total luminosity of the electromagnetic universe. And this particular event was about 420 megaparsecs away. All right, now I'm going to try and play this so everybody can be very quiet. Thumbs. Shift the pitch a little bit. Yeah, maybe I'll good idea. So what you just heard were basically the signals that were recovered from these black holes, actually the waveforms that produce those signals. And what basically we're doing with our detector is we're transducing gravitational waves into things that you can play back, sounds that you can play back on a computer. These are the two black hole mergers that we claim as a detection. This one is the one that we think is a black hole. This is the mass spectrum. And what I'm doing here is I'm comparing the known black holes discovered through X-ray astronomy, through accreted matter, with the known black holes from LIGO. A number of fascinating things here. First of all, these are much, much larger black holes than these guys are. Perhaps more interestingly, from the standpoint of astronomy, is that there are about 25 of these, a little bit less. It took 40 years of X-ray astronomy to study these. And these are all black holes in our galaxy. These are galactic black holes. Whereas the black holes that LIGO sees are much further away. And it took us 4 months to see that many black holes. Now, admittedly, these two black holes are no longer around. They've turned into a bigger black hole. But LIGO is a very effective way of studying the parameters of black holes, so I think that's very important. In fairness, the error bars on our parameters are not nearly as good as the error bars on X-ray parameters, but nevertheless, we think this is going to be a really powerful method. So there are a number of implications for astrophysics and general relativity, and there are people that can give talks on every one of these bullet points. I'll just summarize them. This is the first time that we've ever experimentally observed a binary black hole merger, which says that they exist in nature. It says that they merge in Hubble time. And in fact, it may be that gravitational wave detectors are the only way to see binary black hole mergers. There are some postulation mechanisms that they may produce some kind of light, but so far we haven't seen that. It's the first correct evidence for heavy stellar mass black holes. This guy is 62 solar masses. You can see that all of the known black holes from X-rays are much, much less massive. Our detection, if you go through some astrophysics, says something about a little bit about the formation environment. These black holes were probably not too new. They were formed in a low metallicity environment, Z less than a half, perhaps even less than a quarter. And that actually has an implication that if you believe one formation mechanism, basically that you have a binary star system that evolves into a binary black hole system, that the kicks that occur from supernova are not strong enough to basically break the orbit or destroy the orbit. So that's sort of what you get from a low metallicity environment. The rate is about 2 to 240 per gigaparsec cube per year. And with our detector, that turns into somewhere between 1 every 6 or 8 months to 1 every maybe 2 weeks or 3 weeks. When we get to design sensitivity, it's much better than that. As I said, these black holes are pure black holes. They're entirely consistent with general relativity. We look for the deviations in the waveform, and it's an amazing thing in that it's also the first test of general relativity in really the limit of strong field gravity. All the tests of general relativity that have occurred, for example, using binary pulsar systems, which is really still in the weak field limit. So you can look at how much deviation there is from general relativity, either using parameterizing post-Newtonian. You can also, more interestingly, put a limit on the mass of the graviton, or the Compton wavelength of the graviton, and Einstein, the general relativity tells you it should be zero mass. It should be it should travel at the speed of light, kind of infinite wavelength. In our case, we're consistent. We have an upper limit of a very tiny number. I'm going to conclude quickly with where the future is. And the future lies not with just with LIGO, but with multi-messenger gravitational waves. So now the binary black holes, again, we don't necessarily believe that they produce light. People will still look for that light. But suppose you have a binary neutron star merger where you have a matter-rich environment. Well, there you should produce a lot of light. In fact, I said these should produce gravitational waves. There's also a phenomenon called kilonova. There's an optical afterglow that lasts for maybe a day or a week. And so you should be able to see these events, these binary neutron star mergers, not just with gravitational waves, but also with electromagnetic telescopes, visible, radio, X-rays, and perhaps even neutrinos. So this is a picture of ice cube as poles. So by detecting a gravitational wave in coincidence with any of these other sources will tell you that, a lot more information about the source. Now the problem for us is that LIGO is not a very good localizer of events, and you can sort of do the geometry and the math yourself, but if you calculate what the antenna pattern is, in other words, the sensitivity to gravitational waves from different directions, it's really omnidirectional. There's only a few directions where you're insensitive, all right, which effectively tells you that you don't have a lot of localization capability. So you should think of a gravitational wave interferometer as a microphone more than a telescope. But if I have 3 of them on the Earth, and here are my 2 LIGO detectors. Here's Virgo. This is a detector that's under construction in Italy right now. All right. You can basically triangulate. You can basically resolve the time of flight of the gravitational waves by looking at the phase shifts between the arrival times of these events. And if you can do that quickly, and we can do that quickly, you can send alerts out to your friends who operate X-ray, gamma ray telescopes, or optical telescopes, or what have you. Now, the challenge, all right, is that with 3 detectors, well, with 2 detectors, you only get an annulus in the sky, and you can convince yourself of that just by doing some simple geometry. So with 3 detectors, you have 3 pairs of 2 detectors, and there are 2 points where you have overlap between the annuli. One of those points is preferred due to the antenna pattern, the fact that the gravitational wave detector is more sensitive in one of those points than the other. But you're still limited, and the reason you're limited is that the angular resolution on the sky of a gravitational wave network is measured in degrees, and that's just because the aperture that we use is the Earth, and the wavelength of gravitational waves is such that the best you can do over the aperture of the Earth is a few degrees, which for telescopes is a very wide field of view. Most telescopes can do arc seconds in optical, for example. All right, so nevertheless, this doesn't prevent you from doing this. It just makes the job a little harder for the telescope. So we actually did this experiment. All right, we were able very quickly, when we were running our detectors last year, to identify within a matter of minutes, all right, the sky positions of the event. So here's the first event, and you can see it's relatively well localized. This is a projection basically on the sky. We're in the center here. This is the second event, the one in September, and here's the candidate, the one that didn't get physical confidence. And you can see very clearly that there's annuli, that you have this annuli structure. It's not completely filled in here. Because this event is quite loud, in other words, the amplitude was quite high, it had better localization, but you can still put in, this is, I think, on the order of about 300 square degrees in the sky, right? So how do you do better? You do better by putting on more detectors. I've already told you about Virgo. We're working to put a detector in India. That's just been approved last February. And then there's also a detector in Japan called Kagra. And they're very much like the detectors, the LIGO detectors. And so to compare what you can do, this is actually the real sky map of the GW 150914. The thing that I showed you on the earlier graph is mainly this point right here. All right, and again, I apologize, it's hard to see, but you can see a number of little tiles here. And those tiles represent different telescopes that were used to follow up this event. Now I said we could get these events out in minutes. In fact, it took us days to get the alerts out because we wanted to make sure we had all the information right. But you can see a lot of this area was covered by optical, by X-ray, by radio, telescope. Not surprisingly, nothing, no coincident electromagnetic event was found, again because they're black holes. But you can then do something further, and you could say, if I bring on 2 new detectors, the Virgo detector and the India detector, and I take this error box, and I assume that those 2 detectors are working at the sensitivities that they're supposed to, and I just do a simulation, what you see is that this big blob down here, which is, I said was about 375 square degrees, goes down to 9.3 degrees if you just bring Virgo on, and it goes down to 7.8 degrees if you bring on India, and it even gets better if you bring on Hanford. So basically the idea is as these new detectors come online, we'll be able to more precisely locate gravitational wave events, which means that telescopes are going to be much more likely to find in the electromagnetic spectrum if a signal comes from. So that's exciting. So where are we going? Well, we have to improve the sensitivity of our detector. This was our design, this was our sensitivity during the first run. This is our projected sensitivity. Actually, we're doing a little bit better down here, a little bit worse up here, during a run that's going to start very soon. Ultimately, we expect to get to, with the current detector, we expect to get to this sensitivity level. And then we'll play some tricks that will get us to even higher sensitivity. And yeah, so let me, sort of the last thing I want to say is that in addition to LIGO and other gravitational wave detectors, we are very much a high frequency detector. There's also LISA, longer wavelength, this is a space-based antenna. Radio pulsar timing measures gravitational waves that have periods even longer. This looks for supermassive black hole mergers. And then basically cosmic gravitational wave background can also be detected by its imprinting on the microwave background. So all of these things are now working. Now we've discovered gravitational waves. This will happen in 2030. This is going on right now. This is going on right now. So this new field of gravitational wave astronomy is really evolving. And I think I'm going to go quickly through this. But basically, our grand goal is to have a new generation of detectors, even beyond what we have now, by basically using the simple formula for strain, by making arms that are, instead of 4 kilometers long, making them 40 kilometers long. All right, we'll be able to probe out to, this is mass spectrum, this is redshift. We'll basically be able to probe with a new generation of detectors out to the edge of the universe when the first stars were formed. So we'll be able to see every binary black hole merger that ever existed. And the time scale for this is on the order of maybe 15 years or so. So this is really quite an exciting frontier. And one of the things that's important is that we know in the US we'll have something called Cosmic Explorer. We're working on designing that now. In Europe, there's the Einstein telescope. The network needs a third site, and I think it would be very interesting. We've actually had some modeling of sites in Siberia that might be interesting for this. So this could be very, very exciting. So here's the group of universities and institutions that work on LIGO. I'll close by thanking my colleagues at the LIGO Laboratory, the LSC, also Virgo and the National Science Foundation. Summarizing very quickly, LIGO has made the first detections. We're going to start running very soon, and I expect that the next few decades will be quite interesting for this field. This is very, very exciting. So I'll stop there. Thank you very much.
Impressive presentation. And a couple of questions. Actually, we have enough.
Thank you for your talk. Have you a hope to find by LIGO merging binary neutron stars and supermassive black holes?
Do we hope to find binary neutron stars? Yes. The rates for those are such that we probably wouldn't detect them until we make our detectors more sensitive. Supermassive black holes merge at very low frequencies far outside our detection band, so no, not for that.
Dr. Lucas, from Professor, my question is very simple. Do you know the paper which was published in Journal of Modern Physics this year, number 7, July? The title of this paper was...
Microphone.
The title of this paper was Ligas gravitational wave detection F+ alarm or not?
Is this the paper by...
If you know this paper, you know.
Is this the paper by Ruffini?
This paper is by Policarp Ulyanov from Brazil. CO2 male from China and Ping Yu from USA.
So the answer is,
know this paper?
I don't know that exact paper. I do know that there have been a couple of claims that our detections were spurious.
Excuse me. По-русски скажу. Знаете ли он работу, опубликованную в журнале Review of Modern Physics этим летом, 7-й номер, и которая звучит следующим образом. Является ли детектирование гравитационных волн корпорации Лига фальшем ужасным или нет? Авторы являются Поликарп Ульянов из Бразилии, Мел из Китая и Пинг Ю из Соединенных Штатов.
Какой ответ?
Ужасно.
I know there have been a couple of speculations that we've seen.
This paper was shown that all these phenomena that are...
I will certainly read it.
В этой статье, так же как и в статье, опубликованной в журнале «Инженерная физика», тоже в 8 или 7 номере, показывается, что все явления, наблюдаемые корпорацией Лига, полностью описываются обычными земными процессами в Соединенных Штатах.
Perhaps I can talk to you afterwards and we can go over this.
Let's think of that process as imeni. No problem. Okay. More questions?
Построить дом сложно, а сломать
Nature. Okay. Thank you very much. So, let's see your next presentation will be given by Professor Physicical.